there he is. Awesome.
We have special guests. That's good.
I'm just gonna switch over to this. And so basically today we're just gonna quickly talk about building codes, where they come from, how they get adopted a little bit, and then we're basically gonna dive right into where do they apply the most area of application, the inspections, where both the engineer, designers, and the contractors deal with the codes the most, where they come up. And some we're going to go over some really good example of good craftsmanship that will really go a long way. And then we will answer any questions that anybody might have. So that's basically what we're looking at. So basically, anybody and everybody in our trade at least has some idea about the codes. They're formed to protect safety, health, and well-being of both the public and the residents of that building, the building occupants. So the building must be safe, both for people who live in there and for the general public. And it applies to existing construction or rehabilitation, anything such as that, or new construction for that matter. So there are 4 general areas of codes: building codes, electrical, plumbing, and mechanical codes. And they all come to play with solar and solar thermal, solar PV. Doesn't matter what kind of installation that we do. With solar thermal, definitely plumbing has a much, much bigger role, usually speaking. So, Bob, do you want to go over a little bit about, I think we look at the building codes, what trumps what, basically,
Well, the trump is on any building, on any code, is safety.
It's always
That's
safety,
always
right.
safety. So the codes are designed to, all of them, electrical, plumbing, mechanical, and the structural, are designed for the well-being and safety of the occupants. Then from there we go to energy conservation. Those codes are they're somewhat incorporated in some of the codes. There's also specific energy codes that have usually state they're incorporated into state legislation or state entitlements to what for energy conservation, so you don't build a house that's going to cost you more than the mortgage. That's the reason. And over the years, these energy conservation codes have been tightened or been more energy, to save more energy. So every year or every couple of years they close the gap on or increase the amount of energy conservation you have to provide in a building. Sustainability is kind of falls into the energy conservation. Couple things that they want the house, and it goes back to building too, they want the house to be able to the structure to last many, many years, and to have a low as we call it, carbon footprint energy usage now. That's the new terminology. So the codes they all kind of work together. They're catching, I think a lot of them are catching up, so they do fit together. A lot of these codes are incorporated by the architects, especially in single family construction. Multifamily, the architects are also involved in, and then some engineering is also made. Specialty engineering come into play. Large buildings are, those are general architects and engineers that are doing those. Again, all of this, the pyramid comes into play with any structure that's built.
So the code adaptation, basically, the federal government wash their hand off of this, basically delegated to the states, and then the states basically deal with local jurisdiction having authorities. It's your county, it's your city, it's sometimes even your HOA might, enforce some stuff that they adopted. So it goes into all this little tiny subdivisions, 40,000 plus subdivisions, political subdivisions that adopt and then enforce different codes. So usually my understanding from my conversations with you is that the local adaptation of any code or any energy regulation, any standard that they decide to do, has to basically improve upon whatever is adopted by the state, correct?
Generally, yes.
Okay.
Yeah.
So they just improve upon that. They, for example, like city of Santa Monica, for instance, in California, might decide to have more restrictive energy conservation measures, and
they can to a point.
To a point,
yeah,
right?
it's got to meet or exceed
Meet
state standards. There's also code, various subsections like hospitals that have their own codes to build, so they're more restrictive than the building code. There, OSHPD is the authority for hospitals, which again, if you're building a hospital, that's the codes you're working with. So these are some of the resources we have in the code.
so yeah, these are some of the major organizations basically that come up with the codes. You were talking about the one that comes up with the codes for hospitals. Unfortunately, I don't have that one up here, but again, any number of different organizations come into play to create the codes, and they draw on the experience of the industry across the globe, basically. All the engineers, MEPs, design professionals that are involved, they come together to put their experiences together through this professional organization, such as the International Code Council, National Fire Protection Association, the International Association for Plumbing and Mechanical Officials, and then, of course, ASHRAE, the American Society of Heating, Refrigeration, and Air Conditioning Engineers. And all this combined experience, expertise, and field experience basically comes into developing new sets of codes and new sets of regulations and standards that are then eventually picked up and adopted by different states and then different jurisdictions.
Yeah, all these the 100,000 professionals are also, there's, additional contractors can submit questions, requests, and if it gets through, there's committees and all of these organizations that can look at them, and they can vet the requests or suggestions, and then some of those are adopted into code. Sometimes quickly if there's something that someone missed, and sometimes it goes through the normal process, and on the next cycle that suggestion is now implemented as part of the code, and it's reviewed through the standard procedures that the code.
How does the cycles usually work, Bob? Like, for example, for instance, I see in front of you, you have the uniform code.
New code, nice and gold plated.
Nice and gold plated, all ready to go for you. That's by IAPMO, and that's the Uniform Solar, Hydronic, and Geothermal code that you're using.
Right.
And my experience is, my understanding for that is that also dabs into the IAPMO plumbing codes and stuff like that. And
the code,
that,
well, a lot of the items in these codes come out of other code books. They come, or they're adopted into the specific uniform solar code. This has got a lot of useful information in it. It condenses a lot of things that are out of the plumbing code, the mechanical code, and those are the two codes that IAPMO deals with, and also some building issues, structural issues that are in the ICC building codes are incorporated in this code. It's usually, these codes are adopted every 3 years. The codes change. The cycle is 3 years. So this code is brand new, out in February. It's not adopted by all jurisdictions. That's the one key item that has to happen. They could, a jurisdiction could adopt it immediately. They could say, well, we'll wait for our inspectors to review it, and sometimes they'll take things out of this code and adopt them immediately and use the previous code, and then finally they'll get to adopting the code. And then, of course, as we all know, AHJs have the ultimate authority. They can modify or tweak something or not consider something. That's their ultimate authority. And so every 3 years, all the codes, and some of them are in different cycles. I think some states and organizations do it in a all together, but usually they're offset because the people that are doing some of the plumbing codes are doing the mechanical codes. It just they don't have enough time to keep them all in the same phase. Correct. So we're all on different wave cycles, 3 years apart.
So basically, we're just going to dive right into the major areas that all these codes, the building code, the mechanical code, electrical code, plumbing code, all these will come into play in one way or another in this 13 major category. So the first thing that we have to pay attention to, and it will come up if it's a solar code, if it's the local energy efficiency adopted regulation, right. The collector location and the orientation. If the building inspector, if the city inspector gets on the roof, if they have, if they're inspecting the solar thermal system or the solar PV system, and you live in the US and they go down your roof and you have all your modules or collectors, pointed toward north, all, racked beautifully, they will definitely raise a question and be like, oh, did you inspect the location? Did you, get a compass out to make sure which way these are facing? So that's the one thing, and the orientation of the orientation, actually, there are several different factors because there's a minimum tilt angle that we have to have for water runoff and debris runoff, and then there is the orientation angle that you need to basically adopt to optimize the performance of the collector. So all these will come into
right. There's equipment minimum requirements on tilt, so they drain, they don't pool water. The orientation and tilt and all that is usually part of the energy codes and the calculations that are done to provide the necessary points in the energy code calculations for the solar. So if the solar is the wrong orientation, as Amir has pointed out, then the inspector is going to go back and look at the plan set and say, wait a minute, they're going to say it's wrong. So that's where those two they come into play as far as codes go for usually energy codes. The mechanics of it, don't matter. But you just won't get any performance out of it. It's like having a refrigerator without a door. You won't get performance. So that's where those two things come in. And you can see in the drawing we have orientations, and then you get into the structural mounting.
I can go all the way back to orientation.
Yeah, facing south, the tilt angles. Yeah. All that's done in calculations. There's solar calculators we use, PolySun, F-chart.
Yeah,
and then the Title 24 has their own, which is California for California.
For California Energy Code Title 24, basically they have their own calculator. And my understanding is in the new Title 24 calculator, will have a new solar calculator built into it, which is supposed to be better and more advanced than what we're currently using. But one of the factors that it will take into account when we're running the basically the simulation to show the solar fraction for that Title 24 calculation is the orientation of the collector and whether or not it's facing south. If it's facing south, at what angle, at what tilt angle it's facing south, and that is one of the most important determining factor for that energy calculation result that we see. So that definitely plays a role, and also the location. I think I will further get into it, but it will. In more commercial buildings where you have this large flat roofs, then access, all that stuff will come into effect, then that will be a factor that you have to look into. But before that, this is where the mechanical side of the codes really, I think, plays roles.
Mechanical and building.
And building codes. A lot of times we see we submit a design with a certain tilt angle for the array, and then the architect gets back to us and like, what do I need to do to lower the tilt angle, for example, from 30 degree to 15 degree, and therefore my the height of the structure that I'm installing will not exceed 2 feet or 3 feet or whatever the local limit might be, and they're trying to basically avoid going above that and, not trigger some new structural calculation engineering required for something like that to happen. So these are all different factors. Building codes come into effect here, and then structural codes, mechanical codes will come into effect. You have to keep in mind on large arrays, you're installing a large flat surface area on the roof area where it's like exposed to wind loads from all directions. Right. So Bob has a lot of fun stories about those.
Yeah, that's why we recommend, well, architects on smaller projects are in California at least allowed to do all the structural. Larger projects usually involve a structural civil engineer, and we always want them, to consider the location. It could be here in Fontana where we have Santa Ana winds, 90-mile-an-hour gusts. So you have to, depending on the height, the exposure, you have to design your solar racking to protect against that. If you're in Caribbean, Florida, the East Coast, up the coast from Florida, you have hurricanes. So you have to, again, consider those requirements. And usually systems require structural stamps to be installed. So whether it's a retrofit or new construction, it's all done. I always, as we've seen with the weather we've had everywhere in the country and beyond, it seems to be a little more intense. Some of the codes are changing. I know the wind standards have changed this year, and that's a code upgrade, a code since the last wind, and that's where the architects and engineers are plugging those numbers in. So we always I personally, if you're in any kind of a critical high extreme zone, is to consult with the manufacturer on the solar and make sure that you, if needed, reinforce the system. We don't want it going anywhere in the extreme cases.
Exactly, and that's what we usually end up doing. We basically share the information, the engineering report that we have for our collector mounting equipment or racking equipment. We share that information with the PE working the job, and they use that information basically to apply their local weather data, their local wind data, and make sure that the structural, either they determine our racking system sufficient as is, and they use it, or they recommend different reinforcement to be,
just as
applied.
An example, you can see in the picture it has two points of mounting, which would be onto a substructure base on the roof, like raised beams, I-beams, bond beams. It could be posts with unistrut on smaller projects. We'll show some of that. I mean, you may need to put, like in the Caribbean, you may need to put 3 legs, or Florida, you may need to reinforce quite a bit. Even then, the best you can do may not be enough, but, what do you do if a hurricane hits and it's 140 miles an hour? Hopefully it just kind of falls apart on the roof and doesn't go anywhere. You do the best you can, but you don't want, under most conditions, you don't want it leaving the roof.
So the next topic that we segue to naturally from structures that goes onto roof is when we want to put the mounting and then the connections to those structures, and that's when we're basically drilling holes and penetrating the building envelope. And again, building codes apply, structural codes
building
apply,
codes, plumbing codes apply,
plumbing codes, and then energy conservation codes apply depending on where how big of a penetration you're making, stuff like that.
The energy codes would be insulating the piping. Penetration codes for the flashings, that's all building code or plumbing code, usually building code, some mechanical code, but you want to make sure you waterproof all your penetrations, both the mounting and the plumbing into the roof. That's all. There's plenty of flashings that work and companies that make all the mounting, plenty of them out there, including us.
Yeah, and then we talked about when we talked about the placement of the array and the placement of the equipment, different areas, access, both for service, for inspection, and just generally speaking for safety of everyone. You have to be able to provide access to a point that the service professional is able to operate and see all the valves, all the gauges that are in, like we can see, for instance, here in this image, we have all the different gauges clearly marked where they're going so they can read the temperatures, read the pressures, and make sure the system is in optimum operation status. Same with the array on the roof, and then the roof is again the safety concern for the person who's inspecting the system, for the person who's servicing the system eventually down the road. You know, we recommend, for example, on a regular basis for the collectors to be washed and be free of any debris or any dirt buildup to basically not to impede the solar absorption of the collector. So you have to give that access to that person to be able to wash your collectors, maintain the collectors, make sure they're in optimum working conditions.
Right. Access is also one of the things that come up is access to electrical panels. People, they forget they need 3 feet. So that should be not always caught in plan check because they don't, plan check may not show us electrical service panel or something in there. So that's something that access has to, especially in the mechanical room, you don't want to block any electrical access per code. National Electric Code spells that out clearly.
Another thing, this is then has IAPMO plumbing codes written all over it, and then anything else. But everything else also applies. You know, if you have plumbing, if you have pipes, insulation always comes to play. If you have plumbing and pipes, it means you've done penetration, you have done load bearing, done different areas. Everything, you know, it's all interconnected. There is nothing that doesn't trigger a lot of different aspects of the code. So the storage tank, depending on, for instance, if it's rated to be installed outdoor, indoor, depending on
retrofit. In new construction, usually all the requirements for the structure are met. Floor plan, if these are going to be above ground, or it's structurally sound. If it's on the ground floor, the footing, the foundation is strong enough, the pad is strong enough to manage these tanks. I mean, if you have an ASME tank of thousands of gallons, there's a footing detail that's done for those, and again, it's all covered in plan. When you're retrofitting, example, if this was upstairs in a 3rd story, hopefully that floor that it's on, the room it's in, a couple things that it's rated to handle the weight, and that any, you know, in retrofit, you've got a lot of things to think about. Leakage, is the room sealed for water? Is there drain? Is there adequate drainage?
You can see here they use this big pan here to basically make sure to catch any.
Because some rooms are converted to they may have an empty storeroom. On the ground floor, is there a drain there? If there isn't a drain, are you going to waterproof that entire room in order to prevent water from going under the sill plates and going into living spaces? So a lot of things that you have to consider. Also, fire penetrations. If you're penetrating firewalls, you have to make sure you use the right fire caulk and seal all the pipe penetrations or electrical pipe, any kind of penetration through the wall to code, to fire code. That's a building code, but again, fire. All that retrofit is a lot of details you got to cover. Usually, again, in new construction, all this is covered in plan check and plan review.
Usually those are caught, yeah, correct. But one thing I realize is a lot of time, again, depending on, especially on retrofit project, not paying attention to the placement of the equipment they're using. A lot of indoor pumps being used outdoor, and that always get called by the inspector. They don't like seeing that because obviously that pump was not constructed to be exposed to the element over time, and it will create problems. So there are rated and basically approved solutions that can be used to house that piping outdoor. It's just finding that right solution to make sure you still going around the constraints of your project. You're still making that happen, but then you're still adhering to the code, you're still adhering to the standard that is required basically for that job.
Yeah, retrofits are, I mean, if you just, we're in Southern California, if you go on roofs in LA, there's all kinds of circulator pumps on roofs that aren't covered. Just can't tell you how many.
Mm.
But the when you're doing a job and it's code, it's going to be, it's inspected, pumps outside, you may have pumps outside. You have to, my recommendation, deal with it in planning, talk to the inspector. What kind of housing can I put over the pump to protect it from, direct rain or splash and not be a full, and it doesn't generally need to be a NEMA enclosure that seals it up. It's just you don't want water splashing onto the pump. It would be the same as a pump indoors in a mechanical room and you have a leak. There's nothing protecting the pump there, and you basically what's going to happen, the pump's going to, if it was bad enough, the water would get in there and short the circuit. But so we're just trying to protect the pump, kind of like a tent over the pump, so that it can be, one, protect from water and have the pump raised up off the roof so it can't flood, and then also to be able to, for detachment and pull the covering off for service if necessary. But that's one of the items that come up on retrofits a lot.
Next thing, we talked about the city of LA right now. Heat transfer fluid and heat exchangers. They get called on a lot, depending on the jurisdiction, depending on the inspector himself, depending on the plan checker. A lot of jurisdictions don't like to see single wall, single barrier heat exchangers. They like to see double wall vented heat exchangers, so there is almost zero chance of any cross-contamination happening within the system. They try to really prevent that from happening. Then the type of the heat transfer fluid that you use. A lot of time we call these systems, for instance, indirect glycol system, but then the type of glycol fluid that you use, it really is important depending on your jurisdiction, depending on how it's being used, in what combination of, is it being used with a single wall heat exchanger, double wall heat exchanger. All that matters a lot. So definitely you need to consult your local jurisdiction, make sure you're adhering to that. The cost difference is definitely considerable. If you're going from a single wall heat exchanger to a double wall heat exchanger and braze and plate heat exchangers, large one, you're looking at double the price almost. So sometimes you have to be very much aware of that and what is accepted, what's not accepted. And generally speaking, I think in all the images that we had so far, the quality of the workmanship is always a huge factor, I think, especially during the inspection. Obviously, during the plan check, nobody can see your workmanship, but in the inspection, if the inspector walks into a room that's clearly labeled, kept clean, everything at least looks that was attempted to be built with the best workmanship in mind,
Up to standard.
Up to standard, the chances of them actually passing that inspection is much, much higher. And even if they come across something, they will not treat it as malevolent. They will just assume it was an honest mistake done by an honest person who was doing a good job. So that always matters a lot.
Yeah, all definitions, just get to this, definitions are in the book on heat exchangers and heat transfer fluids. Some of the heat transfer fluids are subject to interpretation. Potable water is one.
Potable water, industrial water, what's the difference?
Some of the jurisdictions have their own definitions, which that's their prerogatives. So a single wall heat exchanger in the code, it's defined, but then the fluid is also defined, and they kind of, there's a zone there that's in the twilight zone. It's not quite defined in both aspects. So even though you might have water on both sides, and one is potable, and that's the one they want to protect, the other water may not be considered potable. It might be considered, some considered industrial. In design we use water as a heat storage medium, but because it's not being used, circulated, or replenished, some jurisdictions do not consider it as a proper fluid to use in single wall heat exchangers. So
they don't consider it as a food grade or safe,
right?
For for being in direct, not direct, but immediate.
With use of a single wall heat exchanger, that's it. I mean,
you have one barrier that if you penetrate that, then you have cross contamination. So that's why, even if that's water sitting in a storage tank and a heat exchanger is running through that, it also has water in it. They might consider the water that's sitting in the tank because it's stagnant. They might consider that as industrial water. So again, it all comes down to your local jurisdiction, what they basically interpret from the definition that they're in different code books. So
yeah, you could use one way to get to mitigate that is with backflow preventers, but those present other annual or inspections. So that's one way of satisfying some AHJs. But the double wall heat exchangers are accepted everywhere.
Yeah, that's a safe bet. Yeah,
when you're using fluids that are considered non-potable or don't fit into the definition that the code states as generally regarded as safe. That is a subject to interpretation. We'll just leave it at that.
Let's do that. And then talk about pipe insulation. So pipe insulation matters obviously because you're trying to keep as much as heat that you gain from the system, and you want to transfer that to your storage tank so you can use the energy later on. That where matters really. So then I think pipe insulation is also covered under multiple different codes, right? It's plumbing, energy
codes, building codes,
fire codes. I bet.
When you penetrate, when you have to maintain a fire break, and
definitely
requires specific insulation. Also, you can see pipe insulation is only as good as the jacket that it has outdoors. We go on numerous jobs many years later, or not even many years, and the insulation has not been coated properly or jacketed. That's what we like. And the sun, just like it does for your house, if you have wood, it wears the paint off and you need to redo it. So, but with jackets properly installed and the right jacketing material, the insulation will last for as many years as it needs to,
for sure.
Which is as long as the jacket. So unless the jacket's damaged, the insulation, as long as it's installed properly and rated as far as temperature goes, it'll last as long as the solar will.
Yeah, so definitely jacketing, especially in high radiation areas, high solar radiation areas, Southern California, New Mexico, Arizona, Texas. In those areas, if the insulation is not jacketed, it won't even last 6 months. The sun will just beat through it in no time, and then.
And birds love it in the spring for their nests.
So they like insulation too, of course. We don't. Okay, the other factor, very important, something that will come up, is safety devices within the system. I think right off the bat, one of the most important safety devices that comes up is the mixing valve. Here you can see it at number 32, the mixing valve or anti-scalding valve installed to prevent water from going to faucet above a certain temperature, usually at 125. We know for a fact that scalding can happen within 10 seconds of contact at 140. So this is a real dangerous thing that can happen if it's not installed properly, if it's not installed by a professional. So definitely that's something that inspectors, plan checkers, designer, professional, they all look into that. Other than that, in pressurized system, if you have an indirect glycol system, probably another important thing is your expansion tank. It will definitely come. And then the pressure relief valves are very important because if you have a closed loop system, that's being exposed to a source of heat, you want the pressure to be released at a safe at a safe rate before it can create further problems.
In the picture, for a closed glycol system or a closed system on the solar circuit, you have number 6 and number 8 are your relief valve and expansion tank. Then you have 22, which is its standard temperature pressure relief valve on this solar tank. Those are safety devices, primary safety devices. And then 32, the mixing valve. This drawing again is residential. Most residential systems do require a mixing valve. Commercial is a little different. That can vary based on design. So, but you don't want to scald, in any case, you don't want to scald anybody or have your solar tank could be 140, 150, and you don't want that going directly to a fixture.
For sure not. And then, as Bob said, you know, that changes completely when you're going from residential application to commercial application, industrial application, when you're looking for low-grade steam, stuff like that. You still have safety devices introduced into system design into your system, but it just works a little bit differently. Another thing that I personally consider as a safety device are definitely the gauges that shows the pressure and the temperatures within the system. Right. Because if you have the digital controller, yes, you're getting readings, but what if the sensor is not working properly? Having a gauge and analog there that you can actually look at could be really useful. And depending on the design, that can again change. But those, I think, are also very important as far as safety and proper operation of the system is concerned. Move on to the piping. Piping, again, something super important. It matters in multiple different aspects. The proper operation of the system is definitely a function of the piping. For instance, if not the proper diameter of the pipe is selected to feed the water to the collector, if you don't have the required flow rate, your system will not operate at all. So definitely the piping codes, the plumbing codes play a role, and Bob knows all about that.
I'm gonna, because this piping does come up with inspectors, and generally the piping for the solar aspect of it, the solar circuit, is done by the designers or the installers, and that the inspectors are, I mean, generally they just assume that that's correct. They're not there to see that the system works. That's your job as the engineer or installer, that you designed it properly. So hopefully you've designed it properly. Sometimes they will, though. They'll say, well, what's the velocity through the pipe? They'll, you know, they'll call you on that, and you have to, you know, you may have to do the numbers and produce the flow rates and velocity through the diameter of pipe you're using. So they may do that. Where we do see some issues are in the potable side. The solar equipment, the tank storage is feeding usually a main boiler, main primary heater, and if the plumbing is not sized properly there, the concern is flow and pressure to the building. So it's been called out with some of our contractors in the past. They say this is too small. So what they had them do, they've made them put in a pressure balancing valve that when there was a high demand, it would open up and provide full flow to the building. That's the number one thing we don't want to do on that side of a system is compromise, impact the flow to the building per the plumbing engineer, or the pressure to the building and fixtures. We do not want to, you know, compromise that. If you're using an ASME tank, the most common systems that were out there in the past, water flows, the cold water goes through the tank and then to the boilers and out to the fixtures. Usually the tanks had 2.5 inch diameter inlets and outlets. The flow was, you know, the engineers compensated. There might have been a 1 to 2 psi drop at the most through these big tanks. When you have different designs, you may not even impact the flow. You might, we call them injection systems, kind of like a boiler works with a surge tank. The water doesn't flow from the city through the boiler and out to the fixtures. It flows through a surge tank, which has big ports, and the boiler is constantly heating that tank as through a thermostat and control system. So it's constantly reheating the tank as cold water is coming in. So the surge tank is for like a high initial demand, like 20 people 30 people come into the apartment, all take a shower. They have that standing water, it's ready to go, and as the water temperature drops, the boiler kicks in and starts reheating the water. So that's what our injection systems are based on that. They don't impact flow to the building or pressure. Works out. We never get calls on that from these are commercial jobs, or in some instances when you have 30,000 square foot Beverly Hill mansions that are built, you do it there too, because they're using, I mean, literally 2.5 inch and 3 inch pipe. That's what unbelievable what you see. So in residences, you may also do injection systems to avoid.
Depends, right?
It all
depends on the design.
Yeah, you just don't want callbacks for those. They're very simple issues to deal with, but you don't want the callbacks, so you deal with them up front. So,
another thing that will come up for the collectors, definitely we'll see this for the tank, for the auxiliary unit, is service connection and isolation valves. Personally, one of the most interesting things that I saw in a commercial project not too long ago was an inspector who required an isolation valve, a set of isolation valves actually, on each individual collector within the array. So each individual collector had isolation valves that could be completely isolated and taken out and serviced. Usually have isolation valve for an entire bank of collectors that we can basically shut off a bank. For example, if you have an array of 3-4 banks, we shut off one bank, the rest of the array is working, and then we're performing service on that specific collector, on that specific bank of collectors. But that's the whole purpose, that's the reason behind it. It's for service purposes, it's for replacing a broken collector, replacing a leaking tank, something like that. That's why you have to have this isolation connection and service connections designed into your
individual collectors being, if you have 50 collectors and every collector has to have isolation on it, to isolate each individual collector, that's
excessive.
Very excessive. If a bank of collectors, 6 to 8 collectors on those banks, or you might call them arrays in PV, those, yes, you can have isolated, isolatable. And then if you have, obviously, if you have shutoffs on something that can produce heat, you have a relief valve in that circuit that cannot be isolated. So
same thing with the example that you see here. It's a bypass that we install on our residential hot water stations. So hot water stations are pre-plumbed, completely built solar storage tank that have all the equipment that you need to operate the system already installed on it. Part of that equipment that we want to include is a bypass, basically assembly. So the bypass assembly allows the tank to be completely isolated from the potable water loop. The potable water will still flow freely from the main to the auxiliary unit, whatever it might have been. It might have been a tankless water heater, it might have been a conventional gas water heater, it might have been an electric water heater for all we care. But by turning these valves in the correct configuration, you isolate your solar storage tank, and you still have hot water because the water going to auxiliary is going on because of the bypass, and you have time to replace the solar storage tank, replace the heating element, the anode, whatever that needs to be done. So that's another thing. Just be aware of it. Inspectors will call on it. The plant checkers will call on it, and it's required by different codes.
Yeah, that's similar to having commercial water heaters. You have, let's say, 300-gallon water heaters, and each of them you can isolate one and run 2 and change the 3rd one, and then so you don't disrupt the entire hot water system to a building. So that's what the isolation on the tanks allow you.
For sure. And then pump control and proper system operation. So as I said, pumps will be looked into, pumps will be called up. If you're using a cast iron pump on your potable water side, guess what? The inspectors, the plant checkers might catch it. They will call it out. They will have you change it. Then the controls also, our experience, especially with solar differential controllers, the amount of knowledge out there is very limited. But then there are specific cities, specific jurisdictions that know a lot about that's what they require and what they want to see. there are some, you have to keep in mind, some of these regulations, some of the the codes will also be tied into different incentives that might be available. So the proper operation of the system will come into play, because the incentive program wants to see the actual savings that was resulted from installing of the system. So if you don't have a proper control system, proper system operation, you can't show savings, and therefore system monitoring comes into play, whatever you choose to use. And then there are different jurisdictions that actually do require system monitoring for a certain amount of time for commercial systems that were subject to incentives.
Right.
I know Massachusetts was one that had that rule.
Yeah, some commercial buildings want the owners or the entity that's putting the system in want to be able to monitor their system. So the control systems usually, well, they have some certification, usually UL or equivalent, CSA and other, and you have to, submit the documents to in plan check, and they're usually, if there's a question, they'll call you out on it. Usually CSA with CAUS labeling is fine, UL listing is fine, but a lot of solar controllers, the actual control is more like a thermostat than it is a control, in that there's no excessive voltage. The voltage passing through these controllers is usually 1 amp or 110 volts, or 2 amps if it's 220, so it's very low power running through them. So when you're running larger pumps, you usually have relays that the controller will activate, or contactors if it's large pumps. So the control is just the mechanism, like an air conditioner. You have a little thermostat and it's cooling the entire office building. So that's what these controls are generally, how they're configured. They're not configured for direct power transfer. You use relays and the appropriate UL listed electrical devices to do all that.
I mean, we are at the Q&A section. I think we did share a lot of good information, and I completely understand if people who are watching don't have questions at this point, yeah. But definitely.
I'd like to mention one other thing that's come up in inspections, and it's related to PV, photovoltaics. There's a lot of systems going in, and then when solar thermal comes in there, some jurisdictions are clueless, or the people that knew about it have all retired years ago. And one of the things that comes up with solar thermal that may or may not apply is bonding and grounding. Solar thermal systems generally use a UL listed pump that's plugged in, powered through the normal circuit, so you have neutral, ground, and power leg, or 2 power legs and a ground. So all of that, and it's all UL listed. What happens is, in bonding and grounding, is that the inspector might say they want the system bonded, and you're going, how do I bond a solar thermal system? Well, generally what you would do is talk to them. You can the piping is copper. If it's connected to the piping in the structure, it should be bonding, grounding there already. If there's a question about that, you just bond jumper your lines to properly bonded piping or code approved, and you take care of it that way. Items on the roof, I think it's a jurisdictional thing. I guess if there's where bonding may be, like bonding of what? The solar collectors, that's the only thing up there. The only time you may do that is if you're in a high electrostatic area with lightning, and you may want to bond things and run them to a ground to prevent, minimize damage from a lightning strike. I mean, if a lightning hits anything, it's difficult to protect it all, but that may be where bonding may fit in, like the South, Florida, but generally it's not required. If you're grounded in your electrical components that you're using, and your piping is connected to a standard piping system, then there's no very rare that you need to do that needs to be done, but some jurisdictions they're transferring PV bonding and grounding to thermal. It's not quite the same. The plumbing is isolated from the housings of the solar panels, and there's no electrical generation. We're not generating any power. Electrical generation, that's not happening.
Yeah.
So that's the one key thing. There's no potential of the solar collector throwing a spark to the metal on in the piping or the collector, because there is nothing there. It's thermal.
Yeah, definitely. So I think I'm getting a question from Robert. We're definitely gonna hold on for a moment. And, definitely, I encourage everyone that, you know, if you have any questions, you can always get back to either me or Robert, Bob, shoot your questions. Email us, because a lot of times, for me, it happens that I go to a presentation and then I'm thinking about it later on and I'm like, oh, what about that? You know, what if that happens? Or what if, you know, something else comes up? And please, we love to talk about solar thermal. We enjoy talking about it, truly. So this is our contact information. Please send us emails, call us. Let's talk about solar, you know. And the codes are constantly changing. What is adopted, what is being enforced is always changing. So it's always good to talk to your local jurisdiction, be involved with your local organizations.
Oh, absolutely.
And they will help you stay on top of your code, stay on top. We just last week, Bob did a really good presentation for the IAPMO chapter here in Long Beach, in Southern California. And we went over all this uniform solar, hydronic, and geothermal codes. So usually if you're part of those organizations, they have this kind of presentations that provide this information.
Yeah, and a lot of feedback back and forth where you're talking to code officials, installers, heads of companies,
directly connected to the protection kit.
Yeah,
Awesome. Robert is pointing out that in Florida, which is a high lightning area, the buildings by code, they already have lightning protection built in, and the bonding cables can just easily be connected to those built-in protections on the roof. So that definitely, yeah. I mean, as you said, in areas like that, probably those jurisdictions already adopted those solutions and those protections in place. So we can easily just bond to those and make sure that everything is properly bonded. Thank you so much, Robert, for sharing that. But definitely, that's why it's good to be part of this kind of conversation. As we saw right now, Robert shared this great piece of information for anybody deploying the system in Florida. So again, thank you everyone for joining us today. Thank you so much for taking the time. Such a pleasure when me and Bob were preparing this stuff for you. So we enjoy doing it. Thank you so much, and we'll hope to see you all again next month.
Okay, thank you guys. Enjoyed it. You did a good job.
Thank you.